for more people to arrive. And then I'm going to show you, I'm currently in the Atlas control room, or next to the Atlas control room here at CERN. So it's a little bit of an impromptu live. This is an Ask Me Anything. I'm going to show you around some of the things we have here, but I'm also going to use some of these facilities that we have in the visitor center here for the Atlas control room to show you what we are working on here at CERN. So any questions you have, please let me know. If you are joining later and you, oh, sorry that the camera's a bit shaky. I should hold it a bit steadier. If you're joining later and you have questions and I didn't answer them during this live, then stick them down in the comments and I will come back and answer as many as I possibly can. Or please do come and join me on a future live. And if you want to do that, you're going to need to subscribe to my channel so that you get notified whenever I go live, because I do schedule lives and then sometimes I just feel like chatting with you and talking about our research, and I will just do an impromptu live. So for those ones, you are going to have to come and join me on my channel, subscribe, in order to be able to be notified as soon as I go live in order to join those ones. So welcome. If you are joining, please do let me know where you are joining from. I'd love to find out where in the world people are joining this live from. And if you have questions, as I said, please drop them down in the chat, because this is an Ask Me Anything, and I would like to answer your questions here at CERN. So hi, I see we've got hellos in the chat already, so welcome. Well, thank you so much for joining. And I am here at the Visitor Center for the Atlas Control Room, and I'm going to show you around the room that we have here and answer all of your questions. So hopefully we'll have some more people joining very soon. So this is a very nice picture that we have of our detector. So I can't go underground right now, that's a shame, because the LHC is running, which is a good thing, and so we cannot be underground while the Large Hadron Collider is running. So we have a question already. How many upgrades are possible to the magnet coils, 1 or 2 generations? I'm not 100% sure which magnet coils you mean. Maybe, hi, Bob's here, welcome. One of the magnets that we have a really nice prototype. I can't go too far because I'll lose the internet. But this is one of the prototypes of the toroid magnets that we have underground in the Atlas experiment. This is a superconducting magnet, which means that we can put 12,000 amps through this magnet. It has to be cooled to 4.9 Kelvin, which is 4.9 degrees above absolute zero, the coldest temperature in the universe. And it has essentially no resistance through it. That's part of the superconducting properties, but only when it's very cold. So I'm not 100% sure which magnets you're talking about. These ones, if we wanted to upgrade them, we'd have to take them out and completely replace them. But thank you so much for the question. If you want to add a sort of follow-up in the chat, then maybe I can answer even better. So somebody says, you've probably answered this already, but why is CERN closed during the winter? So this is a great question. If you don't know already, then we regularly shut down the Large Hadron Collider and the facilities here at CERN during the winter. And this is because we do want a period during the year where we are shut down so that we can go underground and perform any light maintenance that we need to do. So we schedule it at some point in the year. And because we get our electricity mostly from the French side, and a lot of people need to heat their homes in the northern winter here in the Geneva region, then we tend to turn off in the same time when a lot of energy is being used to heat homes, just so that we don't put an extra load on the electricity system. So that's why we tend to shut down over the winter. And also a lot of people here celebrate Christmas because of a lot of people celebrate Christmas. And so it's also nice that some people can take holidays during the shutdown for Christmas, but I don't think that's an official reason. It's just a nice coincidence. So somebody's asking, what happens if you go underground when it's running? So this is honestly one of the only dangerous things that can happen at CERN, and that is because there is something called synchrotron radiation that happens when you have high energy charged particles, and if you change their direction, they do spray off very high energy photons. and these can then hit into other things and spray lots of particles around. So it's just a lot of residual radiation in the sort of cavern of the detector, which is 100 meters underground. So then there is a radiation concern if you're next to it when it's running. It's not very healthy for you. But we have a lot of safety systems. And in a couple of minutes, I'm actually going to show you the CERN, not CERN Control Center, the Atlas Control Center, which is where I am right now. And we have a safety officer that is monitoring the access underground along with a lot of other safety monitoring that they're doing just to make sure nobody is underground. But we also have a lot of automated systems, which means it is not possible to get anywhere near even the elevator to go underground. By the time you've gone through one of the restricted doors, the Large Hadron Collider has already dumped the beam. It's removed it from the tunnel, which means that it's perfectly safe then to be, I mean, you wouldn't be able to get underground before the Large Hadron Collider has already removed the beams from the tunnels. So we have a lot of safety systems here, just to be sure. But that's also why it's 100 meters underground. But right now, I am above the Atlas detector, and I am perfectly safe up here. I spend a lot of time directly above the accelerator and the detectors, and I have no concerns. And we even wear, I'm not wearing mine right now because I don't need to be, but we even wear dosimeters to check our radiation exposure if we're going to any of the regions where there could be radiation. You don't necessarily get any exposure, but it's just to be extra cautious. So thank you very much for the question. And yeah, let me know where you're joining from if you've just arrived. My name is Clara. I am a particle physicist working at CERN. I work on the Atlas experiment. I'm employed in the Netherlands for the University of Amsterdam and with NICEF, but I spend a lot of my time for my research here at CERN, which is where I am right now. And I'm outside the Atlas control room, which is one of the detectors we have here at CERN. And so to give you a sense of scale for the Atlas experiment, I'm going to turn my camera around. We have a very nice Lego model, which since I can't go underground right now, I can show you a bit about the detector with this Lego model. And this model is to scale. So you see these little Lego people? They are the size of person. So I guess the standard is about 2 meters or 1 meter 50. I don't know the 100% the scale, but it's a person scale. And then this is our Atlas experiment. So it's one of the 4 main experiments on the Large Hadron Collider. You can think of it as essentially a giant particle camera. And when the collisions happen in the very center of our detector, then we've surrounded the collision point with lots of custom-made electronics. These are Lego electronics, but in real life underground, it's the real electronics, in order to be able to detect the different kinds of particles. And what I can show you here as well, which is the reason that I'm in this room, is that we have these lovely sort of simulations of the detector. So I can show you the main parts of the detector that we use for identifying different types of particles. So at the very, very center, you can see here in blue, is the inner detector. So this is the region that is tracking charged particles in from the very center, which is the collisions happen right here, and they go off in a sort of firework shape. And the first thing they have to pass through is our inner detector, which you can see is very small, but has a very important role. And then if I click this, I'm pressing buttons, but then we can see some of the pictures from the inner detector. So this picture shows us the pixel detector, which is the very first layer. It's a 2-dimensional imaging detector tracking charged particles when it's going through. And it's located just 3.3 centimeters from the beam pipe. And it has 4 layers of silicon pixel detectors. And if we go across, then this was the installation of an additional layer. So I said there's 4 layers. We started off with 3, and we added a 4th layer. And this is really important to me. I'm just going to turn around for a second. So this part of the detector is very important to me because this is what I did my PhD on. So I spent 4 years of my early research career testing prototype devices for this part of the ATLAS experiment, and then it was installed in 2015 into the heart of ATLAS, and it is the very first layer that particles pass through in our detector when we have a collision. And so it plays a very important role in the tracking of charged particles in our detector, and also having radiation tolerance, because it was an additional layer. That means if any of the layers have any problems, we still have 3 hits, because we always want 3 pieces of information. So it's very cool for me that something I worked on is now in ATLAS and running and taking data and all of that. So that makes me very happy. Okay, and then we can look at more pictures. So I'm not going to go through all of them in this detail unless we have questions. But I think this is one of my favorite pictures of ATLAS. And this is the silicon strip detector. So it is a second section of the inner detector. But then if we go back, press some buttons, but clearly not in the right place. Let's go press it over here. Aha. So now we can go to the calorimeters. But I want to show you where it is in the detector. So now, the next section of the detector is what we call the calorimeters. And these are, if you think of the word calories, that will tell you how much energy or how much heat you get from your food. Calorie means heat. And so the calorimeters tell us how much energy we get from the particles when they're passing through, how much energy they deposit. And so it tells us more information about the particles that are passing through our detector. So we've tracked where the charged particles have gone. We use the calorimeters for working out the energy. And then we want to find out more information about one of the cousins of the electrons, which is called a muon. And the muon, because it travels all the way outside of the detector before being stopped, we have this entire section of the detector. So you now see most of it is blue. That is the muon spectrometer. So that's for detecting the heavier cousins of the electrons, the muons. And we also have a magnet system. So we were talking about magnets. We have 2 magnet systems here. So we have the toroid magnet, which is on the outside, and I showed you the prototype of that outside. And we have the solenoid, which is in the center. So these are 2 very powerful magnets that bend the path of charged particles and allow us to identify information about the particles that are passing through. So very quickly, we can look at some more pictures. So this is the muon spectrometer. So if you ever look at a picture of ATLAS, and I showed you one earlier over there, you are almost certainly going to be seeing the muon spectrometer. So if you also come and visit us when the detector is off, then this is one of the parts of the detector that you'll most likely see because it's on the very outside. Okay, so that's a little bit more about the detector. We also can go back to the Lego model if you have any questions about specific parts of the detector. But let me go back now through some of the comments that we have. There's a great question. The synchrotron radiation is used, for example, as a monitor to know where the beam is and how much beam there is, but not for experiments. Yeah, exactly. So we can use a synchrotron radiation as information about where the beam is, but for the main experiments, it's not what we want to have. So I see that there's also some chat going on in the chat, which is perfect. Very good. What are my opinions on the Large Hadron wrap? I think it's fantastic. So when I first started working at CERN, I can't quite remember when it was released, but it was very early YouTube days. And I think it's a lot of fun. I think it's great to have people playing with being at CERN and having fun with it in terms of like making raps and singing. I think it's really cool that they were able to record that in the tunnel as well, which was very nice. So is it, I'm going to try and pronounce your name correctly. Is it Junit? I'm sorry if I said that wrong, but thank you so much for joining. Welcome to the live. Yeah, and so somebody said in the comments that they've worked with synchrotron where the radiation was the point and used for crystallography. So there are accelerators around the world, that's an excellent point, where the synchrotron is the point of the accelerator, and you can then get a very focused beam of uniform, I think it's quite uniform, right? I don't actually work on synchrotron experiments, but then you can use that for investigating materials. You can use it for doing some irradiation studies as well. So there's lots of uses for synchrotron radiation outside of CERN. But for example, when we collide electrons and positrons rather than protons, because we collide protons in the Large Hadron Collider, electrons are much, much lighter, and so they give off a lot of synchrotron radiation. And this is one of the limiting factors of the energy we can get to with an electron collider. And electrons are very useful because they don't have any particles inside of them. They're what we call elementary or fundamental particles. And therefore, it's really nice to collide electrons and positrons because you know exactly what energy you're colliding at. You know which particles you are colliding. But as I said, the synchrotron radiation is then the limit of how much energy you can get to with a certain size of accelerator. Eventually, it's just giving off so much synchrotron radiation. The more energy you put in, the more is coming out. It's a sort of lost cause, which is one of the reasons there is discussion right now about potentially going to a larger radius future collider or going in a straight line, because then you don't have to worry about synchrotron radiation for electron colliders. For things like protons, it's not actually the synchrotron radiation that's the limiting factor, it's the strength of the magnets holding those protons in place around the circle. So if we want to go to higher energies with protons, we really need to get stronger magnets and or go to a larger radius circle in order to increase the energy and therefore explore looking for new particles with higher energies that we haven't been able to look for at the moment. Oh, so there's a question, am I a scientist? Yeah, so I am a particle physicist. I work on the ATLAS experiment. My research involves top quarks, which are the heaviest particles we've ever discovered. If you've heard of the Higgs boson, top quarks are even heavier than the Higgs. And I also do studies looking at when these two particles interact with each other. I do some machine learning research, so using machine learning to look through the data that we collect with the ATLAS experiment and try to look for anomalies in the data that could be something like dark matter or some other new particle in our data. I do operations work, which means I work here in the control room. So in a minute, I'll go and show you what's happening in the control room because it's nice and busy right now because we are running the Large Hadron Collider and a bunch of other stuff as well. I'm doing some simulation work at the moment, trying to improve our tracking for the future upgrade of the Large Hadron Collider. So we're going to upgrade our Large Hadron Collider. Next year, we're going to shut down for a longer period. There's just somebody who wants to come through the control room. And yeah, we're going to shut down to upgrade the Large Hadron Collider and also upgrade a bunch of our detectors too. It's going to be, I think it's about a 3 or 4 year shutdown. I should know, but I have to look at the schedule again to be 100% sure. But it's a longer shutdown. So we were talking earlier about the winter shutdowns, which is just for a couple of months and scheduled every year. And then after about a 3 or 4 year run in with the Large Hadron Collider, we'll then do a longer shutdown where we really then can open everything up and we can replace entire sections of the detector, for example. So that inner detector that I was showing you on the image behind me over here, the inner detector is then going to get completely taken out. So that bit that I worked on for my PhD is getting removed, but it did its job. So we're proud of that. And we're going to put an entirely new inner detector in that is currently being prepared to go underground. And this is going to be even better, have even more radiation resistance. It's going to have, it's just improved technology that's then going to go in the ATLAS experiment. So that's really exciting. And we can only do that when we have these longer shutdowns. And there's a bunch of other upgrades happening as well with the other experiments, because it isn't just the ATLAS experiment. We also have 3 other large experiments on the Large Hadron Collider, and a lot of other research happening at CERN that doesn't involve the Large Hadron Collider as well, like antimatter studies and nuclear studies on isotopes with Isolde experiment. So there's a lot of really interesting things happening here at CERN that even doesn't involve the Large Hadron Collider. So I wasn't looking at questions, sorry. So there's a question, do you guys use D-shaped particle accelerator? So not anymore. Now our accelerator is a circle, the Large Hadron Collider. But if you would like to see, sorry, I keep getting messages, I should have put my phone on silent. If you would like to see a D-shaped accelerator, you can come to Geneva, if you can come to Geneva, and we do tours every day but Monday. And you can see the first accelerator that we built at CERN. It's now a tourist site. You can get a tour and watch this beautiful light show, and explains how the accelerator works, what research it was doing in the 50s here at CERN, and yeah, learn about the early days of the CERN site and the research that we were doing. So that's a very cool tour that we offer. If you come to CERN, you can also actually come on a tour to this visitor center. So you could be here in person, and it's all entirely free. So if you happen to be in Geneva any day but Monday, you can come and get a tour from us. And we've got a really great museum, and you can meet people working at CERN and ask them questions directly too. So that's all very cool. If you are just joining, then welcome. My name is Clara. I'm a particle physicist. I work on the ATLAS experiment at CERN. So this is my detector, and I'm currently doing a live and Ask Me Anything, just a hangout here in the ATLAS Visitor Center that we have at CERN. And if you like learning about particle physics, please do subscribe. That would really help. Well, it helps my channel to grow, and it helps you to know every time that I go live or that I release a video, so that you can be the first to learn about what's happening here at CERN. So, brilliant. Right. Are electrons a subatomic particle or an elementary particle? It's both. So an elementary particle means it's a particle that cannot be broken down into smaller pieces. But an interesting historical fact that you may or may not know, atom means in Greek indivisible, because they thought atoms were the unbreakable final building blocks of our universe. And then we were able to see inside atoms and see that they're made of protons and neutrons. And then it turned out that protons and neutrons have particles inside of them. So they have quarks and gluons. And as far as we know, these are elementary particles. But it could be that there are even smaller things below those. So that's one of the things we do study here is, are these actually elementary particles, or are there even smaller building blocks inside of them? It's a very interesting question. And so far, as far as we understand, electrons are elementary particles. And they're also subatomic particles because they're in an atom. They make up an atom, even though they're not in the nucleus of the atom. Great questions. How do these detectors work? In my work, sensors change resistor or give a voltage. Okay, yeah, this is, you asked for me to make a video. Sorry, I didn't read out the whole question, but you're asking me how the detectors work. It is going to be a longer explanation to explain the sort of technical details of how everything works, but maybe I can come and show you here. Let's turn around, because one of the beautiful things about being here in this visitor center is that we have some of the prototype devices in this display case. So these detectors work. So here we have a wafer of silicon. I'm not sure if it's focusing properly. There we go. With a bunch of different squares, right? And we can cut some of these squares and we connect them to the readout electronics. And what happens is a charged particle, like an electron, will pass through the silicon device that we put a voltage through, and that will release electrons within the silicon, and then we can read it out as an electric signal. And that is how we are able to know, for example, with the pixel detectors or the strip detectors, that a particle has passed through them. So let me see if I can click this one. So you can see that then this is just one device, and then it gets built into a much more structured device that then gets installed. So we have, for example, over 2,000 modules with silicon sensors, and then they reconstruct the path of the charged particles going through. But it's, to explain even more, then I will need a much longer video to describe them. But I love talking about it because that's what I did my PhD on. And then this cool structure that you see here, let's see if I can pull up the information for that. So this is part of the calorimeter. So earlier I was telling you about the calorimeters that we have, which measure the energy. And so this device, when it's in Atlas, looks like this, which is very cool. And you can see at the bottom here, this is where it's located in the Atlas detector. And it surrounds that inner detector, so it's the second subcomponent, main subcomponent that we have. As you can see in the description we have up here, it measures the energy of electrons and photons as they pass through. And this accordion structure, this honeycomb pattern, it says here that it ensures no particle escapes unchallenged, but it also helps us then with our reconstruction to know the way that the particles have given up their energy. That allows us to identify the different particles that are passing through. So all of this is custom designed electronics that gives us information about the different particles that are passing through our detector. Somebody says the Astro Kobe video was amazing. Yeah, it was really great to meet him. He came to CERN and wanted to go underground, so I was able to show him our Atlas experiment, and he went to some of the other sites here at CERN too. And he was so enthusiastic and such a great person to talk to about our research. And I loved the video that he produced from visiting here. So you can go and check that out after the live if you want to learn even more about what we're doing, as well as look at the videos on my channel, of course, because I make videos about what we do here at CERN. So there's more questions. If the Higgs field is the bridge of the building block of particles in the universe, is it, and the universe, sorry, I'm not reading this correctly. If the Higgs field is the bridge of the, it's the end of the day. I've had too many meetings today. If the Higgs field is the bridge of the building blocks of particles and the universe is expanding, is the volume of energy in the universe increasing? What a great question. So I don't think so. The energy from the expansion comes from dark energy, but we really don't understand enough about dark energy to really say much more than that. To be honest, you'd probably have to ask a cosmologist, because I don't work day to day on dark energy. So I think the energy stays constant, but you would have to ask a cosmologist just to be 100% sure on that. Somebody's asking where I did my undergrad. I'm very happy to tell you. I did my undergraduate degree at the University of Manchester in the UK. So I did a 4-year undergraduate master's degree. So I don't actually have a bachelor's degree. I went straight into the master's and graduated in 4 years with my master's. And then I stayed on at the University of Manchester to do my PhD. And that's when I started working at CERN. So it was the first year of my PhD that I started working here at CERN. So somebody's joining from Texas, from Tennessee. Welcome, everyone. What will I and the other scientists do during shutdown? Great question. Unfortunately, we don't all just get to go on holiday. That's not really how it works. So when we are over the winter shutdown, then often we are looking at the data we've already collected. So it's only a couple of months. And it takes us a very long time to go through the data. So some of the analyses, say if we're trying to learn about the Higgs boson or look for dark matter, these things can take years. So we've still got plenty to do while the detector and while the accelerators are turned off. If you are somebody who works on the detector directly or on the accelerator, then you may use the time underground to do repairs or install new detectors. For example, at my institute, we are part of the team that is preparing the upgrade for the new inner detector that's going to go in during the long shutdown. And so during the shutdown, when we have it, we are going to be finalizing that construction and then moving it to CERN and installing it underground. So that's an incredibly busy period. And often you'll find scientists that do different kinds of work. So for example, I did my PhD on the detector. Very much started off as a hardware person. I spent time in the clean room. You could see me sometimes in the full clean room gear. and I was testing these devices, I was irradiating them and doing very much hands-on hardware research. And now I've kind of moved completely to the other side, well, not completely because I'm not a theorist, but doing data analysis, machine learning, simulation work from the data that we've collected with our detector, and I also do operations work. So you'll get people that maybe just do one or another of this type of research, and sometimes you get people that sort of dabble, and I say dabble lightly, in a lot of different areas of the work that we do here at CERN. And so during the shutdown, I could be helping with the installation underground, and when we're running, I could be analyzing the data. So we all keep very busy. There's lots for us all to do. What kind of somebody's asking, what kind of things do you need to study to work in a place like this, where they do the physics experiments? So if you want to be a physicist, you really need to study physics and maths. These are the two best subjects that you can study in order to be a physicist here at CERN. You should also do programming studies. So if you can code in Python especially, this will help you out a lot in becoming a physicist here at CERN. If you want to be an engineer, then you're going to want to focus on engineering at university. And we have different types of engineers. We have technicians, so people who are really hands-on. They work with the detectors. They spend a lot of time underground when we have the cavern open. And they have a lot of very technical studies. Again, probably maths, maybe physics would help you there, but doing an engineering degree or an engineering internship, so you don't have to go to university, that will also help you a lot. But it's not just physics and engineering. We have computer scientists here, people that are completely working on the computing side of things. We have firefighters here at CERN. If you want to come and be a firefighter at CERN, you're already a firefighter, then we have programs for them to come here at CERN as well. So there's lots of different career opportunities, but really if you want to be a physicist, you got to study physics, maths, focusing on things like statistics, and a bit of machine learning will probably help you now, and definitely on coding. So there's some great discussion in the chat. How long have I been working at CERN? I have now been working at CERN for over 15 years. So I started here at the beginning of my PhD, and then I have been placed in many different research labs or universities around mostly Europe. So I worked, after I did my PhD at Manchester, I worked near Paris in France. I then moved to Göttingen in Germany. Then I went to Nijmegen in the Netherlands, and now I'm in Amsterdam. So I've been employed by different universities or labs, but always connected with the Atlas experiment, always being associated with CERN and doing my research at CERN. So I've moved around quite a lot. You don't have to always be here physically at CERN to do research with CERN, but I've always been on the Atlas experiment since I started my PhD. Some people move to different experiments. Somebody's asking, is Steve Goldfarb still at CERN? I was following Hang Out with CERN years ago and the program stopped. Yeah, so Steve is a good friend of mine. I actually had a meeting with him yesterday where we talk about science communication every week. He's definitely still at CERN. He is now part of the CERN. They have a podcast called Early Morning Coffee at CERN, E=mc². So you should check that out on the CERN channel, on the CERN YouTube channel. Then you can see Steve in the early morning coffee at CERN along with some other colleagues talking about the research that we have at CERN. So it's a kind of renovated version of that Hangout at CERN you used to see. So thank you so much. Somebody gave me a tip. Sorry, I've only just got to it. That's very kind of you. Is it Escrivo? I'm very sorry that I've said your name wrong, but I really appreciate the donation. And you put a question with that as well. So I already answered this one. What should we study if we want to work in the same area you work on? So I think you were the same person that asked it before. But yeah, if you really want to work in physics, then doing physics at university is how you then become a physicist. But what I really want to emphasize is you do not have to You do not have to be employed by CERN to be here at CERN. So as I was kind of saying earlier, I've never been employed directly at CERN. Most of the physicists working on experiments like ATLAS and the other collaborations are not employed directly by CERN. They are employed by universities around the world. So the best thing that you can do if you are choosing either a university to go to or a university to do your further advanced studies like a master's degree or a PhD is to look for a university that has a physics department, obviously, and is doing particle physics research. So if they're already doing research at CERN, then that's going to be an excellent opportunity for you to intern with that research group and get some experience working with them. So for example, if you're in the Netherlands, and we have a number of different research groups in the Netherlands who are working at CERN, and you could do your master's degree with us, for example. But there are people all over the world. We have over 100 different nationalities working in the ATLAS experiment. And if you are open to relocating, then there are opportunities abroad as well. So don't only look directly at CERN, look also at the research labs and the universities that are offering training, and often they are paid. So for example, if you come and do a PhD, again in the Netherlands or places like Germany, you are paid to do that research. It is a job as well as a training opportunity. So make sure you check out sort of paid opportunities to do this research as well. And if you are an undergraduate, you should absolutely check out the CERN Summer Student Program. This will be opening up in the winter in the Northern Hemisphere, so it's going to be around November, December that the applications open up. And I will also be doing some either videos or some hints to help you now with your summer student applications, because I've been talking to people who work with summer students who would like to share some hints with you about your application. And again, that program is paid, so you should 100% apply for it if you're eligible, if you're an undergraduate in the right fields, to be able to come and work at CERN. So I will definitely tell you more about that. And yeah, if you have more questions, you can come find me on Instagram, and I share often in my stories opportunities that are coming up to let you know about what's going on there as well. So thank you so much again for the tip and for the question. What is the most exciting answer you would like to find on these experiments? I very much would love to find out what dark matter is. This is the biggest thing in my research career I would love to be a part of. I would absolutely love it if it turns out that dark matter is a particle, that we can create it in our experiments and we can learn more about it on a sort of fundamental building block level. And then that will tell us more about how our universe works out in the cosmos. Because particle physics and cosmology, astronomy really sort of help each other, we inform each other about how the universe works, but on completely different scales. We're looking at we're sort of diving in to the structure on the smallest scales, and they look at the impact on the broadest scales, and then these two things are very linked. So I would love to know what dark matter is. That would really be a highlight for me. So yeah, if you are just joining, welcome. Yeah, my name is Clara. I work at CERN. And currently we're just chatting and I'm answering questions and I'm showing you around the Atlas Visitor Center. Please do subscribe if you're not subscribed already, and then you can come and find my videos and find out when I do live streams. So what I want to show you before we carry on with more questions is I want to show you where I am here at CERN. So I'm in the Visitor Center. I've already been showing you the screens that we have over here. I showed you this nice picture. You've been seeing the Atlas logo in the background. And now I want to show you, so I can make this transparent. And we have the control center here for the Atlas experiment. So these are the teams that are right now working on collecting data with our experiment. I already pre-warned them that I was going to be filming, so they know that that's why I'm pointing a camera at them, so they can see us as much as we can see them. So right now, I can see that we have stable beams with the Large Hadron Collider. Can I zoom in? Oh, I can't. Oh, that was too much. So this is what we call page 1 at CERN, and this tells us all the information that we need to know about the Large Hadron Collider and the other accelerators. So I stare at this page quite a lot, and the main thing that I want to see here is at the top you can see it says proton physics, stable beams. So that is telling me that we have started colliding with the Large Hadron Collider. Everything is nice and stable. And yes, the magnet, so there's a comment in the chat, the SBS magnet was repaired yesterday. So yeah, and you said all you can see is dizzying numbers. Yeah, when you first look at this, it seems like quite a lot of information, but you get used to what you're looking at when you're staring at that screen. And yeah, so these are all the people. There's a bit of bright light. I have to come stand over here so we can see exactly what's going on. So what we have in this control room is you can see different islands. If I use my finger to point, there are different sections of desks, and each of these desks are doing a different job. So the folks over here at the back-ish, in the middle, they are the shift leader, the run manager, the run controller. So these are the different people who are, so the shift leader is kind of in charge for this shift. They're going to keep working until 11 p.m. tonight and then hand over to another shift crew. The run manager is kind of in control for, or is in control for the week and keeping track of everything that's going on for a week. And then we also have people who are keeping track for years. They're kind of a step up. The run controller we can't really see right now, but, oh no, yeah. The run controller we can't really see right now. They're at the back, and they are controlling the Atlas detector. So they're the ones that are sending commands to the Atlas detector. And then each of the different islands that we have, so we have this one at the back is in charge of muons. These folks here are in charge of the calorimeters, so they're keeping track of that. These folks here are doing the inner detector, and the ones right in the back over here are in charge of data acquisition that we call triggering. So it's making sure that we are getting as much great data as possible from the collisions that are happening in the Large Hadron Collider. And then there are a lot of screens that we stare at every single day to kind of keep track of what's going on here in the control room. So you can see, and yeah, somebody said it looks kind of chill. It is chill because it's the protons are colliding, the detector's running nicely, everything is working smoothly. It shouldn't look hectic in here because we know what we're doing with the detector, and everything is nice and calm. Everybody's an expert, they get lots of training. So there's a question in the chat, did some astronauts work at CERN before? Yeah, so there's a guy, Schwabash, who he was working in the CERN control center, so he's working on the accelerators as an engineer in charge. And he is sort of on leave from CERN, as I understand it, and he's going up to the ISS. He's doing his quarantine right now, and he's going to go up to the ISS very soon for a short-ish duration mission to the ISS with the European Space Agency as a Polish astronaut. So that's very exciting to have one of our colleagues who's going to go up to the ISS. So I'm just sort of showing you the control room, and then we're going to let these folks go back to work. And somebody's saying, are kebabs still the best food around CERN? I haven't been for a kebab in a little while, but there is a good kebab over in Champs-Élysées that many CERN people go to. There's also a great kebab place in Geneva if you want to venture into town for that. So Octavio is saying, I probably won't get a job in physics, but I study it as if I will. It's good motivation. I think it's great to study things even if you don't want to get a job in it. It's nice to learn more about how our universe works. And you never know. I didn't intend to be a physicist when I went to study physics at university. Honestly, I didn't 100% know what I wanted to do in my career, but physics was very fascinating to me, and it had a lot of job opportunities afterwards. I have a lot of colleagues who, or like friends who did undergraduates with me, and they have gone on to be teachers, they've gone on to be bankers, programmers, so many different careers that you can do with physics, because also you have to, it's a very logical program where you have to do a lot of mathematics, you have to do a lot of programming and logic and thinking. So it's a good degree to do if you're interested in it, even if you're not sure what you're going to do afterwards. So thank you again for the very kind donation. So I'm just reading the comment. Oh, there's a really lovely comment that you have to leave, but you really admire the work that's happening here, that the people are doing. So thank you so much for the donation and for joining. I will actually wrap up in about 5 or 10 minutes. Yeah, somebody says that you want to be an astronaut when they get old enough. Doing something like working at CERN is a great way to get into that, because we work with radioactive environments, which also you have a lot of radiation in space, and being able to, yeah, doing engineering is a really good way if you want to be an astronaut as well. So let's have the last few comments down in the chat. Thank you so much for joining me on this live. I hope that you have enjoyed it and that you've enjoyed seeing our visitor center that we have here at CERN. If you're not subscribed already, please do. It would be very nice to see more people around on the channel in general. You jumped on just as I was going to listen to some Gaga, but this was important. I hope you get your Gaga afterwards as well. Thanks so much for joining. I appreciate that I was able to put her on pause for a little bit during this live. Oh yeah, also there was another Swedish astronaut who started as a physicist as well. Oh, somebody's asking, do you use ChatGPT at work or other AI chatbots? So not officially, but I'm sure many of my colleagues have dabbled in it. What we do is we have been developing machine learning for a very long time within particle physics. I've been doing machine learning, which is also, you know, AI. It's what we called AI before we called it AI. I've been doing it since I started my master's over 15 years ago. Back then we were using boosted decision trees, which were a much more simpler version of AI, but it's something that we've been developing directly ourselves, so not necessarily the commercial products like ChatGPT and the other LLMs that you can see out there, but we've been developing our own algorithms directly because we get a significant amount of data from the accelerator, and in order to be able to sift through it and understand it, we can directly train our own AI models, either as classification models, so you can train it to say, this is a Higgs boson in our detector, and this is not a Higgs boson in our detector, and now I want you to sift through the data that we've got and help me to separate between Higgs boson and not Higgs boson. So that's what we've done a lot of as classification work. But my research is also looking at anomaly detection. So if you've ever had a phone call from your bank where they've said, hey, we've noticed some suspicious activity on your account, there's been some spending that doesn't look like you, that's a form of anomaly detection. So they learn your kind of spending habits, where you usually shop, what kind of things you usually buy, how much money you usually spend, and then they can see when there's weird spending on your account, and then they'll phone you up, or they'll just close your account for a bit to check whether or not it's actually you, so that you don't lose much or any money. And for anomaly detection, it's very similar. We can train our algorithms on, this is what we are used to seeing in our detector, either for a specific analysis or more broadly, this is generally what we're used to seeing. And then we can get it to alert us, just separating those data events out, if it sees anything weird. And by weird, it could be that it wasn't reconstructed properly from the detector. It could have been a mistake by our reconstruction algorithms of that data. Or it could be that there's some new process, some new particle, some new force that is giving a slightly different signal in our events and in the trillions of events that we're collecting, the algorithm might say, hey, this one's a bit weird. Maybe you want to look at this one in more detail, and that would help us look for things like dark matter and things like that. So we've been using machine learning, we've been using AI for decades. It's something that many people have also then gone on to contribute to outside of CERN. So they've done some research at CERN and they've gone on to other jobs in machine learning. And yeah, we're also looking at things like, large language models, things like that as well now in the future. So there's a lot of work in AI going on at CERN and in particle physics in general. Bob says, machine learning and AI in physics sounds like an awesome topic for a dedicated live. Yeah, he's very biased because that's also his expertise as well. So Bob's a physicist who was working on machine learning for his PhD. So someone says that they're watching with their son. That's very, very lovely. Thanks so much for joining. So if your son has any questions afterwards, please do send them to me if you want to ask more questions. So there's another question from somebody else. Is the Large Hadron Collider powerful enough to make a black hole to change time and space, even though it's a wild question? So we know that the collisions that we are doing at CERN cannot create a giant black hole that would be any danger to anyone, because the collisions that we are doing are lower energy than natural collisions that happen in our atmosphere every single day and have been happening for billions of years. So we know that our collisions are not going to create a black hole because for billions of years our planet has existed with all these collisions hitting our atmosphere. So we know that we are not going to make a black hole. There were some studies that suggested microscopic black holes could be created, and these are not like those things you see in sci-fi or out in space, these giant black holes. And if they were created, they would fizzle away very quickly. They would just evaporate. And there were some sort of proposals that maybe these would get created in the collisions, but again, they would never be dangerous. But we've not seen any evidence of that. So there's no microscopic black holes as far as we know in our collisions, and even if they were, they would evaporate straight away. And there's definitely no giant black holes because that would have already happened naturally billions of years ago, and we wouldn't exist to make an accelerator to be able to do the collisions. So we know that we're not going to make black holes. So there's a very tricky question here. Do you think the scattering angles from inelastic and elastic collisions at the Large Hadron Collider are symmetric about the impact parameter? Like, are these collisions always the same, and what causes the variation? So we get the collisions are always slightly different due to quantum mechanics and other properties of the particles. So sometimes you get this nice symmetric collision. Sometimes they come off more in one direction. We do look at trends of collecting billions of events, for example, to see if there's any specific region where the particles go more often than not. Also, because this helps us look for things like we know neutrinos are created in our collisions, and these are not detected by our detectors, and so we get a little bit of asymmetry in our collisions. And if we got a lot of asymmetry, so if there was a lot of stuff missing from our collisions, that would be a really nice hint of something like dark matter. So if we saw a lot of asymmetry, we could then investigate and see that maybe the reason that these collisions, there's more stuff going in a certain direction, is because of dark matter. And then we could investigate that more. So far we haven't seen that, but it would be very, very exciting if we did. Does mass really get increased when we accelerate particles in colliders, or is relativistic mass real? This is a term that kind of gets used, but I'm not personally a fan of. I don't think that mass increases. The energy of the particle increases, and so mass and energy are equivalent, and you can exchange one for the other. But I don't really like the term relativistic mass. So I don't think that mass actually gets increased. It's just the energy of the particles increases. Someone's interested in chemistry and would like to know if it's a good field to pursue for study in a career. I think chemistry is really interesting. It wasn't my personal topic that I wanted to go on and study, but I know a lot of people who are chemists and are doing really, really interesting research in chemistry. So if you like chemistry, you absolutely should go and study more about it if you want to. I think it's a very interesting field. There's Dr. Andre, you should look up on all the social media platforms. He's a chemist and I love his videos, and really inspires people to study chemistry. Yeah, someone says it would have been cool to find Hawking radiation. That would have been cool. Archie, how can I start a career in SciComm at CERN whilst also working as a physicist? There's multiple ways of doing it. You could do it like I do, which is just go ahead and talk to people about physics. I love chatting about what we're doing, and so I will talk to people as much as possible about science communication. But you can do it more officially too. We have excellent science communication teams here at CERN who can support you if you want to do science communication. You can get training in how to write, how to talk with the public. So if you want to know more about that, send me a message on Instagram, because I can give you some more advice more directly. But generally, talking to people every opportunity you get is a great way to practice science communication. Yeah, and then there's some great comments in the chat about the Idea Square and the Science Gateway. So if you're at CERN, it's definitely send me a message on Instagram, and I can hook you up with some people who can provide you with some training and some more advice about science communication. So someone says, so going back, so not one micro black hole has been detected so far, but it's possible in theory. This isn't about you at all. The phrase possible in theory is a really broad phrase, because when you haven't discovered something in physics, the maths might still work out. So yes, it's possible that you could still get a micro black hole, but we've never detected any. So then we set limits on the likelihood of it happening at all, or the likelihood of it happening and us having detected it. So saying something is possible in theory, there are a lot of things that are possible in theory, but very, very, very unlikely. And so I'm not saying for this one, but like in the lifetime of the universe, it's not going to happen. But it can still be possible in theory, if you know what I mean. So yeah, I think... Oh, excellent. So you'll be coming to the Netherlands for your master's, hoping to visit CERN as well. Come and visit us at NICEP if you're doing your master's in the Netherlands, and we can definitely help you with science communication. So I can see that we're coming up to the hour mark, and I think this is a great time to end this live. I'm going to go and get some coffee and some dinner, but I really, really appreciate you joining me for this live. Thank you so much. It's been a lot of fun chatting with you and answering the questions. I hope you've enjoyed seeing our visitor center here at CERN. I may come and do more lives here because it's very useful to have, for example, a very nice Lego detector to explain things with, and also check out my colleagues who are in the control room right now. Although I spend a lot of time in that control room, so it's almost like a second home. Again, I really appreciate your questions. If you're not subscribed, please do subscribe. If you have more questions and I didn't get a chance to answer them, please do drop them down in the comments of this video, or if you're watching this video later, please do drop your questions down in the comments, and I try and come back and answer as many as possible. And yeah, it's been really great chatting with you. Have a great rest of your day or evening or morning or wherever you are, and I will chat to you again soon about our research here at CERN. So there, thanks for joining.